It's been a few weeks since my last upload to the channel, and I wanted to make a new video for a while, but I couldn't think of really anything to say. These past 4 weeks have been kind of just a whirlwind of responsibility, papers, presentations, grading. Oh my gosh, the grading. I think in that video I talked a little bit about all the things that I'm doing this semester, which I don't really want to rehash, but just know it's a lot. Like, I'm taking 2 classes, technically 3. There's the seminar, the stats class that I don't know anything about stats. So I have to learn the material along with them and then grade 100 students' papers. I mean, there's not 100 papers, but they work in groups, but it's 100 grades I have to input into the grade book. And if I give out a grade that someone doesn't like, which these days turns out to be like 9 out of 10, then more often, sometimes I'll get it, not often, it doesn't happen that often, but sometimes I'll get a student that will say, hey, how come you took off 1 point? And I'll say, well, you didn't really show your work. And then I have to like argue with them. Well, not argue, but you get the idea. A lot of students don't like to show their work in a math class. It's commonplace. One time long ago, I had a student. The guy was really smart, and he was like an A/B student. But I would always take points off his stuff because he wasn't showing his work. And I talked to him. I was like, "You really should, write down the arithmetic." He goes, "But I can just punch it in a calculator, get the answer." I was like, we need a little bit more than that at this stage. Anyway, he told me he was dead set about not showing his work. I was like, all right, more power to you. But he did well in the course, even still. But yeah, there's grading, there's teaching. I teach 4 days a week. I have to be in the library for like 5 hours to do this tutoring session I signed up for, which I'm not complaining. I do like sitting there and helping people, but sometimes, when there's 5 people there and they're asking you like, how do you find speed of a car over an interval of time? I'm like, it can be a bit much sometimes. I started this video wanting to be positive, and I ended up just focusing on the negative. So that freaking beeping, you probably have heard it like 5 times or so now, I can't count. But that is my smoke detector. That smoke detector's battery is about to die. It's been in hospice now for for months. But in the last 2 weeks, I emailed my landlord saying, hey, there's a beeping smoke detector. Can you come please change the battery, or someone can? And they're like, sure. But then there was like an emergency, so the maintenance crew said, all right, we'll get back to you. And it's been like 2 weeks. Supposedly, they're supposed to be here tomorrow and change it, but I've been living with that beeping for 2 weeks now. And it's kind of got a permanent residence in my mind, almost. Like, one time I was walking to campus and I thought I heard it. I was just crossing the street and I heard beep. I was like, no way. No way. I did hear a beep, but it wasn't in my brain. But I'll be glad when it's gone, because it's hard to sleep with that thing. And before you say anything, like, I can't reach it, I don't have a ladder. My ceilings are very high in this apartment, and I don't have a ladder to reach it, and I really don't want to buy a ladder just to turn off a smoke detector, because it really only takes like 5 minutes for them to come up here and change the battery. And then, like, I don't have to mess with it for like another year or so. Anyway, that was a really boring story about a battery. Where in the world are the measure theory videos? They're still being made. It's a big undertaking, and the fact that this semester is as big as it is, like as busy as it is, makes it harder to finish and do what I want it to do, how I want it to be. But I'm right around halfway, probably a little bit more than halfway done with the individual chapters of it. But they'll still get done. They'll still get done. It's kind of overwhelming being a real adult now, You know, you think you're a real adult when you're in your 20s going to college, and then you realize when you keep going down the, you know, whether you're climbing the corporate ladder, you're going into graduate school, you're becoming a professional, you realize you weren't as pushed as hard as you think you are. Because I have had students in the past tell me, you know, I'm working really hard in the class. Can you see how hard I'm working? I was like, oh, well, okay. How many hours did you study for the tests, for example? And they're like, oh, I studied a lot for the test. I was like, how much did you study? They're like, oh, for like easily 3 hours. and I roast them a little bit. I was like, I studied 2 years for a test. But for them, it's a lot, you know, because, you know, they're like 18, 19. In high school, they kind of just push you through, I think. Because they can't, what are they going to do really in high school? Are they going to like fail half the class and then they have to repeat the 10th grade? And then the 10th grade, you know, grows by like 50%. It's not really feasible. I don't really know anything about high school education anymore. I kind of just went in, did my work, got my A, and then left. But you can definitely see that some students are realizing the game has changed. It's not high school anymore. In fact, I don't know if you saw off in the corner, but a student got me this Dunkin' gift card. Hold on, there's nothing on here that, no, okay. So this Dunkin' gift card she gave me because she wanted to, I don't want to give out too many details, but she needed me to come in on a Friday to help her with something, to help her. And I said, okay, yeah, I'll be there. So she came in, I helped her, and then to thank me, she got me this Dunkin' gift card. If only I drank coffee. But I do like donuts, so maybe I'll get a donut or something when I get there. She's a real nice student. I like students that talk to me. Students that don't talk to me, I want them to, but you can't force them. It's better. Otherwise, you're just kind of up there just professing knowledge, and you don't know how it's going. You feel like a bombing comedian a little bit. Which is why I like teaching the first-year students. They got a lot of energy. They're just out of high school, so they have an enthusiasm. The college hasn't beat them to death yet. And then by the second year, you start to notice that, okay, they're maturing, and they know just what it is they're going to be doing for the next 3 years. So they kind of get quiet, and then they're like, just tell me what it is I have to do, teacher. I'll do it. I'll get it to you. And then you know, you do like that responsibility, but you see a little bit of enthusiasm dissipate from their eyes, which is kind of upsetting. That beep, man, I'm sorry. I wanted to make a video with no beeping, but it beeps regularly, so it's kind of hard to avoid. Anyway, what else can I tell you? It's kind of a scatterbrained video, I know. I should have had the candidacy exam done in the summer, but that didn't get accomplished for a couple reasons. The summer course was very involved. I had to prepare for exams rigorously and aggressively, I guess you could say. There was a lot of sleepless nights, especially right before the exams, to make sure I understood how to do those problems. And some of the homework problems that he gave were really tough. I don't remember if I mentioned it in a video, but my advisor actually looked at some of my homework problems that I got in that summer course. My advisor's a smart guy. He had an article written about him a couple years ago because he solved like a problem that was 100 years old, and they wrote an article about him, and he won like the University President's Award or something for it. Word had circled around about, you know, his accomplishment, his great achievement. So he's a smart guy, and he looked at the homework, and he came to me. He goes, hey, struggling grass. He doesn't call me that. I don't think he knows about my channel. And he comes to me. He goes, hey, struggling grass. How are you? How you doing on that homework? I'm like, I don't know. I'm doing the medium difficulty problems. I haven't looked at the hard ones yet because the homework was built in like 3 categories: easy, medium, hard. And he goes like, let me help you with some of it, because those hard problems on there, those are kind of like, I wouldn't do those. Even he was just like, I'm not really sure how to solve some of these. He goes, I think I know how to do problem number 7, which was one of the hard ones. But problem number 8, he goes, I wouldn't even touch it. He goes, it's too hard, dog. It's too, he goes, just do the medium, because you can get an A in the course if you just do the medium difficulty problems. But, yeah, that was really tough. And then, you know, we had the Spain trip. So I learned a lot in Spain. I took a lot of notes. I really enjoyed the lectures there. I think I'm just summarizing the last video now that I think about it. I don't really watch my YouTube videos that often. That last video, I got like 50 notifications. I know it was from people commenting on it. And I didn't check a single one of them. I didn't want to read what people wrote. There was a part of me that felt like delisting the video, but I said, let me leave it up. I'll just leave it there. Maybe I'll go back to it and watch it. Because again, like, I know that my views are dwindling. I need to do something to reinvent this channel if I want to keep it alive. But really, when I started this channel, it's not about playing the YouTube game. This really is just something that I can look back on and say, okay, this is what I was thinking at the time when I was getting this PhD. And maybe if it helps someone else, then that's also good. So, long story short, summer was super busy. I didn't get to do as much research as I wanted to. And as a result, my candidacy has been delayed. Hopefully this will be the last semester, and oh my gosh, I really do hope it's the last one, because I'm tired of taking classes. This is the busiest semester I've had so far into the PhD program. Depending on the advisor, they kind of set the standards as to what they want you to do for the candidacy exam. And I know that there were a couple people that I came into the program with. Their advisor said, okay, we really need to get you guys. They have the same advisor. He told them that he really wants them out of the classroom so they can start just focusing on the research and trying to get a paper published and something like that. So they did like candidacy like the first week of the semester. And, you know, that's fine. But, you know, it's the advisor that sets the standards. I think my advisor wants me to have like a real paper. Not like a real paper, but like we get some sort of result. So where it's like, okay, this could be its own paper. That's what he's trying to say. Which is kind of hard to do when you're taking all this stuff. But it is the situation. It's the analysis life. What else can I say? I don't know. The classes haven't been, as of yet, too demanding. But it is just, it's not so much like, I know it can get really bad really quick. So right now, the first 4 weeks have been like, okay, I remember seeing this before. I'm taking the notes. The homework isn't due yet. You know, it's kind of due when the test is coming up. And the test has been delayed because the instructor is taking a, he's not going to be here for like 2 weeks. So when during his departure, it's not a break. I don't really want to say what he's doing. But during that time is when I was like, okay, well, now we have to really start focusing on the homework and preparing for the exam. And then afterwards, you know, he might start talking about stuff that I'm not familiar with. Because right now, all the things that I know about topology that I've learned, he has condensed into 4 weeks. So I've been in review mode of all my topology. But in the future, we may start to talk about some things that I am not familiar with. And then I really start to have working. In these 4 weeks, really, I have just been thinking about making sure that my students aren't mad at me, because I want to be a good teacher, but at the same time, my research needs to get done. So that's kind of been my top priority for the last 4 weeks. Anyway, so because I mentioned topology a lot, I thought I would talk about 3 homework problems more or less homework problems that he gave in the class in case you're interested. The first one has been solved. It's we talked about it, and it wasn't really a homework problem. He gave it to us to think about, and then we thought about it, and when we came back, we discussed the solution. And it's kind of an odd statement if you're familiar with elementary topology. You have this topological space, and you have this finite collection of compact sets. The first statement is to prove that their union gives a compact set. Remember, it is a finite family of compact sets. It's not necessarily true for a countable union, like the real number line, for example. You can write it as a union of intervals, closed intervals of finite length. But the second example is kind of strange. Give an example where the finite intersection is not compact. So again, you have a topological space, you have a finite family of compact sets, but their intersection that need not necessarily be compact. And he kind of told us, like, all right, so is it necessarily true or is it wrong? And if you have a Hausdorff space, then I believe the answer is yes, it is compact. It is always compact. But if you have a stranger topological space, then it may not necessarily be compact. And me and a friend thought about it a little bit. We tried playing with it because I thought maybe the statement was true. We started playing with it and realized, it's probably a bit more sophisticated than I thought. And then, you know how it goes. You try and try and try. You don't get anywhere. You're like, all right, let me just go to the internet. And I found a cute counterexample on the internet. So when class time came back, we discussed the counterexample. If you're interested in the answer, I would just go to Stack Exchange. This is on there, rather than have it write it up. Or if you just want to think about it yourself, be my guest. So this one is an actual homework problem that we were given. You have a topological space. You're given a set E. E can be any set in the space. And we look at these two operations, interior and closure. So you have the interior of a set to be the union of all open sets contained within the set E. So you can think of it as the largest open set contained within E, and the closure is the smallest closed set that contains E. So you're taking the intersection of all closed sets containing E. And we want to study all sets of the following form, where we start with E, we can look at its interior or closure, and then you can take the closure or interior, respectively, of those sets, and then just keep alternating back and forth between them. And we want to say something about how many distinct type of sets that we can make here. So the homework question is, what is the most amount of distinct sets you can make using interior and closure? And you can make anything that you want. So the homework problem is, all right, what's the most number of sets you can make using this, idea? And you should give an example of a topological space and a given set E that attains it, and that you can't go any further than that. Meaning, like, maybe the maximum is 7 for some reason. Give an example where 7 is attained and why anything greater than 7 is not possible. And I also make a remark here that if you take the interior of a set, you don't really get anything extra. You just get the interior. And the same is true for the closure. Okay, so that was a homework problem. A friend of mine claims to have solved it. I need to look at his solution. He wants me to check his solution to see if it works. But he encouraged us to talk to each other and try and divide and conquer these problems. As long as we understand the solution, the instructor's fine with it. But again, I've been prioritizing other things than homework right now. But the one homework problem that he did give us that I was interested in, like when he gave it to us, I was like, this is an interesting problem. I think maybe I can do this, is this one. So you have the real number line. It is endowed with the usual topology. You have a function from R to R. Everything's comfortable so far. And we define gamma f to be the graph of the function f, which is the set of all points x comma f of x. So that's the graph of the function, and we assume that the graph is connected. So we have to recall what the definition of connected is. It's about having two open sets, both of them non-empty, hold on, what's the definition of connected? You have two open sets. The set is contained within its union. And you want to make some conclusion like it has non-trivial intersection or something like that. There's overlap between the two. Or one of them is empty. As a butchered definition of connected, but sometimes it might be easier to think of like what it means for a set to be disconnected and reverse engineer the definition. He also, by the way, hasn't given us the definition of connected yet in the class. He gave us the homework problem, and he goes, all right, I'm going to give you the definition of connected next week. But I'm trying to remember vaguely what it says. Okay, so the question is, must f have a point of continuity? So the graph of the function is connected, but does that necessarily mean the function is continuous? And, you read this and you think, it probably has some sort of point of continuity, but maybe not. Because you can construct some pretty weird functions. So this was the idea that I had that I messed around with. I'm not claiming that this is the solution, but it has got me thinking. So if you're familiar with the topologist sine curve, what we have here is we have phi of k defined to be sine of 1 over x minus qk, where qk is some rational number. So I should have written this, but I have some enumeration of rationals, and I can define phi k to be this sine curve translated by qk. And it has a point of discontinuity at the origin, which no matter how I define it at the origin, so here I've defined it to be equal to 0, not at the origin, but at qk, it's translated by that. No matter where I put that point, it's going to be a discontinuous function. But it's well known that this graph is connected. So I have a discontinuity at a rational number, but its graph is connected. So I thought, well, just scale them all by some tiny amount, like 2 to the negative k. Add them all up. Remember, the rationals are countable and dense in the real number line. And I get this weird function f of x. So the Weierstrass m-test can be used here. The reason I scaled it here is because I wanted to invoke the m-test, so that f of x is a proper function in its own right. And now the only thing that I'm interested in is showing whether or not that this function has a connected graph and has a that it's discontinuous on the rationals, but maybe also it's discontinuous on irrationals. It probably depends upon the enumeration that you're given, so there's a lot more to invest, or it may just be discontinuous on some proper subset of the reals. So I'm not claiming that this function works. There's probably something here that's wrong, but this is what I got to play with when I was thinking about this the other night, because I've constructed counterexamples using this same idea, using this m-test, using this, building block function to build something more pathological. But yeah, I want to investigate this more. I showed it to some of my friends. So far, no one has come up with a solution. I know on Stack Exchange, if you change the first R to R2 and propose the same question, then the answer is no. You can construct a function that's discontinuous everywhere, but is also pathwise connected. Or at least this is what this one guy claims on Stack Exchange. He actually gave an explicit form of the function, and he claims it's discontinuous everywhere, but it's pathwise connected, which is a stronger form of connectedness. He didn't prove it, but I'm sure if I played with it, I could understand what he was getting at. It did not look like this, by the way. Anyway, I want to play with this more, see if it actually works, see if it doesn't work. I know, like, for example, what's got me a little bit suspicious about this function is that you have something like the Dirichlet function, which is the indicator function on rational numbers. That function is discontinuous everywhere, but you are able to define a function that is continuous on the irrationals, but discontinuous on the rationals. And it's not the Dirichlet function. That function, I think, has a special name. It's like stars over Babylon or something like that. So this function makes me think, perhaps I should be more careful with where I put these rational numbers and how I put these rational numbers, because it may be discontinuous on Q. That part seems believable to me, but you have to prove it. But whether or not you get discontinuity on the irrationals is also another beast in and of itself. And then you also have to prove whether or not it's connected. So there's a lot here that's not on the paper. I'm just, the reason I'm being thorough here is because mathematicians are very quick to point out, like, nope, that's wrong, you're an idiot for saying that. They have a commitment to the truth, I think, that's unlike any other scientist. But what do I know? I don't know anything. I just know my little corner of the STEM fields. Anyway, I hope you found these exercises intriguing. I'll probably work, at least on the last problem, a little bit more, but I do want to refocus on research and get the candidacy thing done. The goal is October, but October is approaching real freaking fast, and I don't know if I can get it done by October, but I'm going to try my darndest. So see you in the next video.